Uh, hello. How are you? This is the fourth stage of model questions for exit exam or gate exam of chemical engineering thermodynamics 1 by Lata Deso. I'm the lecturer and researcher of Department of Chemical Engineering, HARAMAYA Institute of Technology, HARAMAYA University. So today let us start the questions or the model questions for chemical engineering thermodynamics 1. It says 1 kilogram of water at room temperature is brought into contact with a high temperature thermal reservoir. So depending on this statement, what is the entropy change of the universe? The multiple choice A says it is equal to entropy change of the reservoir is equal to the entropy change of the water is equal to 0 is always positive. So before answering these questions, let us start or let us explain the entropy change of the universe in relation with the entropy change of the water at room temperature as well as the entropy change of the thermal reservoir at high temperature. Initially, let us explain the change in entropy of the universe by utilizing the second law of thermodynamics. Second law of thermodynamics. So we can utilize the second law of thermodynamics to deal with the entropy change of the universe by relating with the entropy change of the reservoir as well as the entropy change of water. So let us look at the entropy change of the universe. The entropy change of the universe can be determined by using or by considering the entropy change of the system, water, and the entropy change of the thermal reservoir. According to the second law of thermodynamics, the total change of the total entropy change of the universe is always positive or zero. It cannot be a negative value. It cannot be a negative value. So, in order to explain the entropy change of the universe, let us see one by one. Since the question directly related with the entropy change of the reservoir as well as the entropy change of the, the entropy change of the water. When the water at room temperature comes in contact with the high temperature thermal reservoir, the heat directly flows from the reservoir, which means that the high temperature system to the water until they reach the thermal equilibrium. As a result, the entropy change of the reservoir is directly given as the entropy change of the reservoir, which is equal to Q reservoir, which means that the heat transferred from the reservoir or thermal reservoir divided by the temperature of the reservoir, where Q reservoir is the heat transferred from the reservoir, T reservoir is the temperature of the reservoir, or it is a high temperature system, is a high temperature system. Second, the entropy change of the water. The entropy change of the water is given by the change in entropy of the water is equal to Q of water divided by T of water. Whereas Q of water is the heat transfer, which means that the heat taking system from the reservoir, which means that this is Q of water, heat of the water, and this one is temperature of the reservoir, temperature of the water, temperature of the water, temperature of the water. So let us connect both entropy change of the thermal reservoir and the entropy change of the water by relating with the entropy change of the universe. Since the water and the reservoir are in thermal contact and the heat is transferred between them. So the entropy change of the universe can be obtained by summing up the entropy change of the reservoir and the water. The summation of both the reservoir, the entropy change of the reservoir as well as the entropy change of the water gives us the entropy change of the universe according to this equation, according to this question. In this explanation, the water at room temperature is directly brought into contact with a high temperature thermal reservoir, which means that the temperature is or the heat is directly transferred from the reservoir to the water because it contains a high temperature, it's a hot temperature. It's a hot temperature. Temperature of the system is high. That's why it is transferred from the thermal reservoir into the water. So the entropy change of the universe as a result, heat flows from the reservoir to the water until they reach thermal equilibrium. Until they reach thermal equilibrium means the change in temperature with respect to the change in T is constant. Since the thermal reservoir is at high temperature than the water, the heat is directly transferred from the reservoir to the water. The flow of the heat is from the reservoir to the water. The entropy change of the reservoir is positive because heat is transferred from the reservoir to the water. On the other hand, the entropy change of the water is negative due to heat is transferred to the water. Directly, there is the flow of the heat from uh, from what we call it from the reservoir to the water. That's why the entropy change of the reservoir is positive. When we sum up the entropy change of the reservoir and the water, we will get the entropy change of the universe, which is directly the entropy change of the reservoir plus the entropy change of the water, which is equal to Q reservoir divided by T reservoir plus Q water divided by T water. So this gives us directly, this is positive, okay? This is positive is positive value. This one is negative value comparison with the entropy change of the reservoir. Since the temperature of the reservoir is higher than the temperature of the water, the heat transfer terms in the above equation is in opposite signs, which means that the first equation, this one is positive, this one is negative. So this indicates that the positive entropy change of the reservoir dominates the system, and the overall entropy change of the universe is positive. Therefore, according to this question, the correct answer is D. The entropy change of the universe is always positive. The second question says compressibility factor of a gas is A. The ratio of fugacity in the given state to fugacity in the standard state. B. The ratio of actual volume to the volume of the gas if it were ideal. C. The change in volume with temperature at constant pressure. D. The difference between the actual volume and ideal gas volume. Initially, let us explain the compressibility factor of the gas. So let us see the definition of compressibility factor. Compressibility factor is a useful thermodynamic property for modifying the ideal gas law to account for the behavior of the real gases. So directly it compares the ideal gas with the real gases. It is a measure of how much the thermodynamic properties of the real gas deviates from those expected of an ideal gas. It studies or it measures the deviation of the real gases from the ideal gases. It may be thought of as the ratio of actual volume of the real gas to the volume predicted by the ideal gas as the same temperature and pressure as the actual volume. Compressibility factor is the ratio of actual molar volume of a gas to the molar volume of it if it were an ideal gas at the same temperature and pressure. So Z which is equal to PV divided by RT. This is normally Z, which is known as the compressibility factor, which relates the ideal gas with the real gases. So depending on this equation, at high pressure, all the gases of Z less than 1 can be easily compressed. Therefore, the correct answer for this question is B. Multiple choice B is the correct answer. The correct answer. The third one is topic explanation. Let us see the thermodynamic processes and the thermodynamic cycles. Let us see point function and the path function in thermodynamic relations and the processes. Point function and the path function explain the thermodynamic processes and the relations. The aforementioned functions are different in every thermodynamic systems. Let us see the difference between them. Point function means when two properties locate a point on the graph or coordinate axis, then those properties are called as point function. Let us look at on the graph. For example, if you wanted to draw the graph of P versus V, you can show or you can analyze the point of V as well as the point of P on the graph. For example, pressure, temperature, volume are considered as a point function or point function. You can manipulate mathematically from their points. It didn't uses directly the graphical manipulation. Graphical manipulation means we didn't manipulate by using what we call it area. It is a point function. For example, if you take volume, the change in volume means the difference in volume from one location to other location. For example, look at this one is the box, which means the thermodynamic relations. Here, and this stage, the pressure is constant, and this stage, the volume is constant. This one is P1, this one is P2. Again, this one is V1, V2. So, according to this explanations or graphical analysis, the change in volume is simply from one system to two, which means that change in volume from or the differential of change in volume from system 1 to 2 means V2 minus V1 because it is an exact differential. It's considered as an exact differential. Second one is, let us see the path function. Path function is directly determined on the graph by using an areas, which means that an areas under a given system. There are certain quantities which cannot be located on a graph by a point but are given the area also on that graph. In that case, the area on the graph pertaining to the particular process is a function of the path of the process is referred to as path function. For example, heat and work are considered as a path function. And in addition, they are inexact differentials. Their change cannot be written as a difference between there and the status. Their in the status. So we cannot write as a difference like a point functions. For example, let us see heat. Since it is inexact differentials, the sigma which is sigma of Q from 1 to 2 is not written like Q2 minus Q1. It can be written as Q from system 1 to 2 or Q1 to 2. Similarly, for the work done, you can write as W2 minus W1 is not the way of writing the path function parameters. So it can be written as work done from system 1 to 2 or work done 1 to 2. This is the difference between path functions. You can determine the area under the graph. It is not a point function. Path function is not a point function. The operator sigma is helpful to denote inexact differentials, then the operator D is used to denote exact differentials. In exact differential, you can find the values of the parameters in between the points, and you can determine the status of the parameters in difference. But in pass function, it is not advisable to find in differential form. That is the main difference between point function in chemical engineering thermodynamics. In chemical engineering thermodynamics, especially in thermodynamic relations and thermodynamic processes. These are the main differences. So let us look. So this is the end of lecture 1. As a reference, you can use Engineering Thermodynamics 1, which is written by Rajput, as well as a textbook of Chemical Engineering Thermodynamics by Narayan. Thank you for your attention.